Hello everyone and welcome back to this online NPTEL course on aquatic geochemistry. In the previous lecture we were discussing about the stable water isotopes and specifically how it varies in the hydrosphere. We started discussing about the oxygen isotopes and the stable hydrogen isotopes, and we just started to discuss about the Rayleigh fractionation that happens during the evaporation and condensation processes in the global hydrological cycle, starting from the ocean to the rainfall and across the entire continental precipitation events up to the poles. Okay. So, this I just want to emphasize if like how more I can emphasize the role of stable water isotopes, that is delta 18O and delta D in our understanding, in generating our understanding of the aquatic masses, and specifically about the physical processes that water undergoes through. Okay. So, what kind of physical processes are happening that controls these two isotope compositions, and by calculating by measuring these two values, we get a lot of information starting from the source to all the physical and the chemical processes and even biological processes. And not only that, so it is not only that, we also get a lot of understanding about our past. So, how it has varied in the past. So, paleo temperature, paleo ocean. So, everything we get to know just from this data set of different kinds of. So, it can be from carbonates, it can be from the water samples itself. So, stable water isotopes, I will be focusing upon this isotope system hugely because of the kind of applications that is had, because of the enormous application it has in aquatic geochemistry. And when we are looking into this kind of global hydrological cycle. Okay. So, for instance, I want to understand, like suppose if I am in India and I am trying to find out, okay, there is a rainfall event currently occurring, then how much of the water masses, like the water vapor masses, is coming from the different sources, say suppose the Indian Ocean as compared to the continental vapor. So, of course, when you are sitting here, say suppose you are sitting here in India, okay, suppose you are here, okay, if you are standing here, then of course, there will be some ocean water vapor, and of course, there will be the small water bodies, okay, so lakes, rivers, groundwater, evapotranspiration, that is also giving out a lot of vapor into the atmosphere. So, it's a mixture, that is condensation is happening and then that rainfall is happening. So, when we are going to ask these questions like, okay, what kind of sources of the water masses could come from, the air masses that came from, what is the vapor source, all these kind of questions we can utilize stable water isotopes as tools to do this kind of source apportionment, like whether it is coming from the Indian Ocean, whether it is coming from the western side of the Indian continent, or whether it is coming more from the inside of the continent itself. So, the different areas will have different kind of isotope signatures. Okay. The signature of the rainfall that will come from western disturbances will be very different from the kind of signatures that the water vapor from the Indian Ocean will bring. Okay. So, this kind of source separation we can very delta 18O and delta D, they are very useful. And when it is raining, okay, we always we are always in a process, we are not the start or we are not in the end, we are somewhere in between. So, we have to type of quantify, okay, what is the isotope composition of this condensate and whether we can go back to the initial water vapor, or we can find out what is the remaining water vapor composition. So, that kind of computations we can also do from this water isotope data. So, how do we do that data? There are particular equations that we can use. So, in this kind of fractionation, the Rayleigh fractionation, we consider that this is an equilibrium fractionation. Okay. This is the first assumption that we make. So, it is a equilibrium fractionation that is happening. Okay. It is a chemically open system. Okay. It is a chemically open system, there is a transfer of mass and energy going on. Okay. Transformation takes place at equilibrium between phase A and phase B. So, whatever is the phase. So, if the liquid is evaporating, there is a evaporation, and from that evaporation again it condenses back. So, this process is at equilibrium. So, when my water vapor is condensing to form the rainfall, that condensation process is at equilibrium. The evaporation process is not at equilibrium. Okay. It is only the condensation process from the water vapor to the liquid form is what is at equilibrium, and they are continuously exchanging the phases. Okay. So, that phase is exchanging, but as soon what is also happening specifically for Rayleigh fractionation is that as soon as the condensation is happening, that condensate, be it in the form of rainfall or be it in the form of snowfall, that is getting removed. So, that is going out from the system. So, even though it was generated during an equilibrium process, after its generation it is getting removed. Okay. So, it is getting completely removed from the system. We no longer are going to get this rainfall back, right. So, as soon as this rainfall starts raining, we are removing it from that system. Okay. So, that phase gets removed from this system. We are no longer going to consider that phase any more in any of our calculations in the further steps. So, the few assumptions that we are going to make is, first, the air mass is a closed system. So, that nothing is again coming inside or going out from that air mass. So, if a air mass is moving, this particular cloud is moving, then that is behaving as a closed system. And often at times that we see that huge when huge clouds formation is happening, then the minor contributions from the terrestrial sources and any other mixing becomes negligible. For instance, during the monsoon, it is a huge phenomena. It's so much of clouds is coming from the oceans to the land mass that the continental evaporation may become negligible. Then the most of the contribution is coming from the oceans. The all other sources of water vapor may become negligible. So, this is one of the assumption. Okay. What is our second assumption? Our second assumption is that the condensate that is getting removed from the system is not going to evaporate. So, there is no re-evaporation of the condensate. Whatever is lost is gone, There is no more evaporation and coming back as in the form of vapor from that condensate. Okay. So, the rainfall that is happening is going to stay in the terrestrial system as rainfall or as water in whatever system, but it is not going to evaporate back and mix with the clouds again. So, this is the two assumptions that we are going to make. First, that the air mass is a closed system, there is no more inputs or outputs from this vapor that is moving inside the land mass. And second of all, whenever the rain is falling, there is no evaporation. Generally what happens is, whenever the raindrops are falling, if the temperature is very high, most of the rainfall will get evaporated in the atmosphere itself. It will get evaporated in the atmosphere and the remaining vapor and the remaining condensate will come down. Okay. But a significant proportion of the rainfall gets evaporated in the atmosphere itself when the raindrops are falling. Okay. So, this is not happening in our Rayleigh fractionation. This assumption we are taking that no such evaporation of the raindrops or of the snowfall is going to affect our air mass. Okay. Given these two assumptions, given these conditions, what is the composition, what is the stable water isotope composition of the vapor, of the initial vapor, of the first vapor. So, this is written in the form of RV0. So, the initial vapor, the present vapor and the present liquid. So, the ratio in the initial vapor RV0, the ratio in the current vapor and the ratio in the liquid that is happening, the ratio in the liquid. So, what is the equation that we used to calculate this the vapor composition, the liquid composition, the initial vapor composition? So, for fractional condensation, what do I mean by fractional condensation? The entire vapor mass is not going to condense at the same time. It is slowly going to condense given the temperature, given the humidity, given the the entire a lot of other parameters when it is going to rain. Okay. So, the entire cloud is not going to release all its vapor in the form of rainfall at a given time. So, this is a fractional condensation process. It is a fractional rainfall that is happening. The remaining cloud goes on, it goes on moving in the other directions. Okay. So, in that condition, under equilibrium conditions, that is, it is exchanging this vapor, the initial vapor, they are all in equilibrium. Then the ratio is 18O by 16O. So, that is my R is equal to 18 oxygen by 16 oxygen, or if I am using deuterium, then I will write hydrogen and 1 hydrogen. So, that is deuterium versus divided by protium. Okay. So, the ratio in the vapor is equal to the initial ratio of the vapor RV0 into multiplied by the fraction of water vapor that is remaining in the air mass, the fraction of water vapor now remaining in the air mass to the power alpha minus 1, where alpha is the fractionation factor between the liquid and the vapor. Okay. So, at a given point of time, the ratio in the vapor is related to the ratio of my initial air mass multiplied by the fractional fractional amount that is remaining. So, the fraction of water vapor remaining, and that is raised to the power of the fractionation factor between the liquid and the vapor minus 1. So, this is a very important equation. Okay. Another important equation that we are going to use is to find out the isotope ratio of the condensate, okay, of the rainfall, of the snowfall that is forming from the water vapor at a given specified fractional contribution. So, this is the rainfall or the snow the snowfall's composition. So, that is a ratio in the liquid. Okay, so, now I am considering it is in the liquid phase. So, that is the rainfall phase. So, the ratio in the liquid is equal to the initial vapor ratio multiplied with that is the alpha, the fractionation factor between the liquid and vapor. That is also again multiplied by the fraction of air mass remaining to the power of alpha minus 1. So, that is my two equations that will help me to understand the remnant vapor ratio, the liquid that is condensing from the air mass at any given fraction, and the initial vapor composition. So, generally what will happen is that we are going to collect this, we are going to collect this rainfall, we are collecting these rain samples. So, from the rain samples we have to find out this, that is what is the ratio of the, or what is the composition, what is the isotope composition of the initial vapor mass, or maybe even this one. Now, once we find out this, we can find out even this, but what is very difficult to assess is F. What is the fraction that was remaining in the atmosphere, because this is, understand, it is in the atmosphere. We are not going to have instruments up there to tell us how much fraction is remaining and how much fraction is precipitating. So, F is a term that we are going to try to remove from our equation, so that we can do away with the dependence on F, and we are going to just use some other equations and some type of substitution if possible, or we are going to find out what is F given some data. So, we are going to find out two things. First of all, what is the ratio in the vapor phase. So, you collect the rainfall as well you collect the vapor. So, both you have, then you can find out another unknown parameter, that is the fractional of vapor remaining. So, for the vapor phase we already know that R V is equal to R V 0 to the power f alpha minus 1. Just rewriting the equation, and in this we write R V divided by R V. So, this just term comes in the denominator, which is equal to f into alpha minus 1. Now, R V by R V 0 we can also write it in terms of alpha term. It is like writing in any fractionation factor, and if I write it in terms of alpha, it becomes alpha V by V 0, right. That alpha, if I write it in terms of delta values, is equal to 1000 plus delta V divided by 1000 plus delta V 0, and this now is equal to f to the power alpha minus 1. So, when I am trying to find out my f, what I need the data of is, I need the data of the delta 18O of the vapor, I need the delta 18O value of the initial water, of the initial air mass, and I need the data of the fractionation factor. Okay, I need the value of the fractionation factor. Now, let us write it in terms of the liquid phase. Let us see how we can substitute and use a get an equation for the liquid phase. So, R L, the ratio in the liquid, is equal to R V 0, the ratio in the vapor, initial vapor, into alpha L V into multiplied by the fractional of the air mass remaining to the power of alpha minus 1. That again I will just do some substitutions and all. So, I will just bring this term down. So, R L divided by R V 0 is equal to 1000. So, this again it becomes that alpha L by V 0, and that can be written in this term, that is 1000 plus delta L divided by 1000 plus delta V 0, which is equal to this term alpha L V into fractionation of to the power alpha minus 1. Okay. So, here I just removed it here, this is the remaining term. So, this term we gave, okay, we came down to this term. So, this term is equal to now alpha LV into f to the power alpha minus 1. So, if I am going to measure the delta 18O of the liquid, so then it comes that the delta 18O of the liquid is equal to alpha into fraction of f alpha minus 1 multiplied by this entire term, because this is now going to go to the numerator. So, delta 18O of the initial vapor plus 1000 and this whole term minus 1000. Okay. So, this is what we are going to get from the second liquid phase. Okay. And now, if we going to use these two equations together, okay, if you are now going to use the two equations together, you can see that this entire term, okay, delta 18O of V plus 1000 into f alpha minus 1 minus 1000 is my this term, right, is my this term. So, what I am going to do? I am going to again rearrange and rewrite, and I am going to get to this equation where I have delta 18 of liquid is equal to alpha LV, in bracket I have delta 18 of OV plus 1000 and the whole thing minus 1000. So, from here I can calculate my vapor 18O. If I am not aware of that, I can calculate that, and I can go on calculating all the other, one by one, okay, all the other unknown parameters. So, this is a very, very important equation. Okay. It is a very, very important application of 18 oxygen of the stable isotope delta 18O in understanding and finding out the source, the source vapors isotope composition, its fractional changes and all that. And how does it, how does it progresses when there is continuous rainfall. Okay. So, here in this particular figure, we have the F in the x axis, that is a fraction of air mass remaining, and this is the 18O of the vapor and the liquid. So, simultaneously we have two two lines, one is for the vapor phase and one is for the liquid phase, right. So, when the entire vapor is there, so 100% of vapor is there, then it is at its most negative, it is minus 10, something close to minus 10. Okay. As the vapor is losing more and more liquid, as there is more precipitation happening, the first precipitation when there is when there is no precipitation, it is very close to whatever is the ocean value is. So, that is very close to 0. As soon as precipitation starts, so this fraction goes down, you will see that from this vapor, this liquid is getting formed. Okay. So, this is the liquid composition, this is the vapor composition. Okay. The liquid is always heavier than the vapor phase, as we have already discussed that the 18 oxygen always prefers the more stable, the more heavier phase, that is the liquid phase, over the more lighter gaseous phase. Okay. So, as the vapor gradually loses its moisture and there are more rainfall events happening, the vapor gradually becomes more and more negative, and the liquid also goes more and more negative until and unless it becomes 0. Even at that point, it can be very close to the final vapor composition, or maybe just a little difference may be there in their isotope composition. So, generally it is like theoretical, it is that the last liquid that is raining from the last vapor is is same as that of the last vapor itself. So, this is how it progresses during a continuous and gradual rain out process. And mind you, the complications can be the re-evaporation of the liquid, that is the condensation phase, back into the atmosphere, because we are assuming in the first place that it is not going to re-evaporate. But often in natural, in natural systems, we know that re-evaporation can become a problem. And also is the alpha value. So, the dependence of alpha with temperature, and when it is raining or as the vapor mass is moving, there can be huge temperature shifts. Okay? There can be huge temperature shifts. So, which alpha value you are going to consider and how correctly you are going to use it, giving all the assumptions and everything, that is a very important decision. So, these are the two complications that can come when we are going to use Rayleigh fractionation in our real life applications. So, given this brief introduction to Rayleigh fractionation, we are just going to shift ourselves towards looking into the whole hydrological cycle. So, we are going to start from the biggest reservoir, which is the oceans. So, the oceans, as you can see, is having one of the largest volume, 1350 into 10 to the power 15 meter cube, and has a delta 18O value of 0.0 parts per mil. From here, evaporation is happening. Evaporation, this much amount is getting evaporated, this much amount is getting precipitated back, close to 90% is getting precipitation is coming back to the ocean itself. But above the ocean, the atmosphere, that has a water vapor content of this much volume, okay, that has a water vapor content of this much volume, and this is the 18O, that is the 18O value of the vapor above the oceans, that you can see is having a slightly negative value, right. It has negative value, indicating that the heavier isotopes remain in the oceans and less so in the atmosphere in the vapor form, and there are more 16 oxygen in the atmosphere in the vapor form. Now, when this water vapor is moving from the oceans to the continents, there can be some rainfall cycles. Okay. So, there will be all this precipitation and evaporation effects. So, due to this, the 18 oxygen will gradually become more and more negative. So, you will see more and more negative values coming in. Okay. So, this is going to give the land value. Okay. So, this is going to give you the composition of the land. So, here the delta 18O of the rainfall or of the snowfall is slightly less, it is slightly less negative. So, here the water vapor is minus 20, but the rainfall, the precipitation will be much more positive, right. So, that will be less negative. So, if this is minus 20, this is supposed to be minus 8 plus minus 7 parts per mil. Okay. Again, there is a continuous evaporation precipitation cycle is going on, but from the atmosphere a huge amount and for a very long time. Okay. So, it is a long term transfer, gets trapped in the ice caps and in the form of the glaciers. Okay. So, imagine this ice caps and glaciers were formed at a time when the temperatures were very cold. Okay. So, this delta 18O value is extremely negative. So, minus 30 plus minus 15. Okay. So, this is having a very negative value, and this is for a very, this is going to get stored for a very long time, and this again is going to, if transferred, okay, if it is going to get transferred onto the land mass, okay, then also it is going to be for a very long time. Now, all the land mass via the rivers the runoff is coming into the oceans, but that is not going to change the ocean composition hugely until and unless the entire ice caps and the glaciers are all melting. Okay. The runoff is not going to alter hugely the ocean until and unless the ice caps, the glaciers, everything starts melting. In fact, it is calculated that if all the fresh water that is locked in the ice caps, that is in the Antarctic, in the Arctic, in the Himalayas, in the other Patagonian glaciers, in the other Canadian glaciers and all that, if they are if they start melting, okay, and if they got completely melted, then the delta 18O value of the ocean would decrease by 0.6 parts per mil. Why is it going to get decreased? Because these ice caps, these glaciers, they are rich in the 16 oxygen, right. They are rich in the 16 oxygen. Why? Because as the air mass moved, from the equator to the ice caps, these ice mass had more and more negative values. So, minus 60 parts per mil, right. So, here 16 oxygen is highest, okay, is more abundant, is very more abundant as compared to the 18 oxygen. So, when I am going to melt all these ice caps into my ocean, then all this 16 oxygen is going to come in. So, 16 oxygen rich from melt water. So, now this is 16 oxygen rich as compared to my 18 oxygen supply. So, therefore, the value of the delta 18O will decrease by 0.6 parts per mil, and it can start having, that is 0 minus 0.6 will give you minus 0.6 parts per mil. Okay. So, this is how the stable water isotope composition is going to change across the hydrological cycle. Okay. Now, how do we get all these data? How do we come to know about all these data? Now, globally we have an entire network of sampling locations, of collaborators who provide all these samples and different kinds of water samples such as rainwater samples, lake water samples, river water samples, groundwater samples are routinely collected for this delta 18O and delta D analysis all over the world. Okay. So, there are specific programs such as the GNIP program, which is the global network of isotopes in precipitation, okay, or the GNIR program, okay, that is the global network of isotopes in rivers. Okay. So, there are such specific programs that is run by an agency which is the International Atomic Energy Agency. They that is in Vienna. They are going to monitor all these locations, they are going to take all the samples, they are going to generate the data, okay, and they are going to use new information and going to because of its huge implications in understanding the climate, in understanding our Earth's history, that we have a central agency that runs all these huge programs. And the number of stations, as you can see, that it was 900 GNIP stations in more than 100 countries, and the number of data it can have is very high at a monthly scale. Okay. So, this is just in 1 month. Okay. This is just in 1 month, okay, the amount of data, and it shows in the color of the variation from positive to very negative values, as you can see. Okay. So, this is the more positive values. So, here in this desert area we have more of the positive values as compared to very negative values close to the poles in the Arctic area and also close to this Greenland, the Antarctica and the Arctic area, and also at locations in the Himalayas. So, this programs, they are run by international agencies, so that we have a far better and robust understanding of these isotopes and their implications in earth science. With this, I come to an end of today's lecture, and we are going to continue about understanding more applications of the stable water isotopes in aquatic systems in the next lecture. Thank you.